If you had infinitely many jars, they simply would not fit in the observable universe, the part of space that astronomers can actually see. It's a strange thought, right? This is the immediate physical wall we hit when we try to imagine the scale of the same concept we use in mathematics. By definition, infinity is something that never ends. It's the total opposite of everything finite, things we can count all the way through to a final number. But here is the puzzle. If two things never end, how can one possibly be larger than the other? Well, today, we're moving away from that vague feeling of boundlessness and stepping into a mathematical proof that fundamentally changes how you see the universe. To understand where this logic begins, we have to go back to the late 1800s. Back then, most mathematicians actually feared infinity. They didn't treat it as a useful tool, but more like a danger zone, because it seemed to break every rule they knew. For the vast majority of these thinkers, infinity was just a concept of boundlessness, not a number. It was like a horizon you could walk toward forever, but you'd never actually reach it or touch it. Now, this created a strange tension, because calculus already existed, and it relied on this very idea. Calculus uses infinity to define things like limits and derivatives, which basically allow us to calculate the slope of a curve at a single precise point. Yet, despite all that practical success, the actual nature of infinity remained a sort of conceptual ghost. It took a specific kind of bravery, or maybe a certain level of madness, to stop treating infinity as a void and start treating it as a quantity. That's where we meet Georg Cantor. He wasn't content with just the vague notion of the endless. He wanted to measure it. Now, to the mathematical establishment of the time, this goal was considered completely absurd. I mean, infinity wasn't viewed as a number, but as a boundary. Most people operated on what we call potential infinity. Think of it as the process of counting forever without ever reaching a destination. It's a direction, not a place. Cantor, however, proposed something far more radical: actual infinity. He argued that we should treat infinity as a complete quantity, a size, rather than just a process. By doing this, he shifted the entire framework. In modern mathematics, infinity is handled as a number because it represents the size of a set. Basically, Cantor stopped looking at the horizon and started measuring the distance to it. Let's start with the most basic building block of this hierarchy, the set of natural numbers. In math, the collection of all counting numbers is our first example of an infinite set. When you think of counting, you're thinking of the sequence 1, 2, 3, 4, and so on. This is what we call a countably infinite set. To be clear, countable infinity refers to any set where you can list the elements one by one. If you can create a one-to-one correspondence, a perfect match between the elements of your set and the natural numbers, you've got a countable set. It's structured and predictable. Georg Cantor gave this specific magnitude of infinity a name, Aleph-Null. Written as the symbol null 0, Aleph-Null is the first transfinite cardinal number. It represents the total quantity of the counting numbers. Now, you might think this is where the story ends, that every infinity is just Aleph-Null. But keep this in mind. This is just the first step on a ladder. Later, we'll see how Cantor's diagonal argument proves that some sets are simply too large to be listed one by one, which completely breaks the logic of the countable. To make these counterintuitive properties of infinite arithmetic feel more concrete, mathematicians have used a thought experiment for nearly a century called Hilbert's Hotel. Imagine a hotel with countably infinitely many rooms, and every single room is occupied. Now, in a normal hotel, a full house means no more space, period. But in this scenario, the manager just asks the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on. By shifting everyone up by 1, they create a space for one new guest. Surprisingly, adding one new person to an infinite number of guests results in the same infinity. It doesn't matter if a finite number of people arrive. The math just shifts. But what happens if a second infinite bus arrives? This is where things get really strange. Two Hilbert hotels, each with infinitely many guests, still equal one infinity. To solve this, the manager asks every guest to move to the room number that is double their current room number. By doubling the room, the manager creates infinite new spaces for an infinite number of new arrivals. The total size of the set remains Aleph-Null. The hotel is just as full as it was before, yet it still fits everyone. Now, let's look at a paradox that seems to defy basic logic. If you take the set of even natural numbers, you'd assume it's half the size of the set of all counting numbers, right? But George Cantor proved that the set of even numbers is actually the same size as the set of all natural numbers. He did this using a simple function, f of x equals 2x, which maps each counting number to an even one. To make this work, Cantor relied on one-to-one correspondence, also known as a bijection. Essentially, a function defines a bijection if it perfectly matches elements between two sets, meaning each object has exactly one pair and nothing is left over. Using this approach, Cantor proved that the set of integers, which includes negative numbers, and the set of natural numbers are the same size infinity. He matched 0 with 0, 1 with 1, and then alternated positive and negative integers with counting numbers to establish the cardinality of this infinite countable set. This logic goes even further. Integers and rational numbers, your fractions, are also considered countably infinite. To prove this, mathematicians use an integer lattice and count dots in a counterclockwise fashion around the origin. This means that whether you're looking at even numbers, odd numbers, multiples of 10, or squares, they all share the same magnitude of infinity. Now we hit the wall. For a long time, mathematicians thought every infinite set was the same size. But Georg Cantor realized that real numbers, the decimals that fill the gaps between the counting numbers, are not countably infinite. They simply cannot be listed one by one. To prove this, he introduced the diagonal argument in 1891. Imagine you have a list of every single real number between 0 and 1. You might think you've captured every possible decimal, but Cantor showed you can always create a new number that is not on that list. He did this by taking a digit from each number in the list diagonally, the first digit of the first number, the second digit of the second number, and so on, and then adding 1 to each of those digits. By changing just one digit for every position, the resulting number is guaranteed to be unique. It cannot match the first number because the first digit is different. It cannot match the second because the second digit is different. This simple, elegant logic proves that the set of real numbers is strictly larger than the set of natural numbers. These are what we call uncountable sets. The set of real numbers is a larger size of infinity than the counting numbers, a scale known as the cardinality of the continuum, which is an uncountable set greater than Aleph-Null. This discovery doesn't stop at the real numbers. To quantify these sizes, mathematicians use the concept of cardinal infinity, which defines the size, the cardinality, of infinite sets. In formal notation, this is denoted by the symbol absolute A. Now we have a hierarchy. Aleph-Null is the first cardinal infinity, followed by Aleph-1, Aleph-2, and so on. These Aleph numbers aren't just labels. Each subsequent Aleph represents a new layer or dimension of infinity. Specifically, the size of the set of real numbers is equal to 2 to the power of Aleph-Null. This is the size of the power set of the natural numbers, and it's proven to be uncountable using those diagonal arguments. Cantor showed that you can build bigger and bigger sizes of infinity by repeating certain processes, like using the power set to find a larger cardinal number. This creates an increasing ladder of infinities, proving that not all infinities are created equal. Emily Real, a mathematician, provides a clear way to navigate this hierarchy. She explains the concept of infinity at 5 levels of increasing complexity, which allows us to climb the ladder of cardinalities without getting lost in the abstract. By breaking down the progression from countable to uncountable sets, Real's approach transforms a dizzying array of different infinities into a structured, logical sequence. It's at this point where the mathematical community moves from proving that bigger infinities exist to asking a much harder question. Is there a gap between the smallest infinity and the next? This transition is where the continuum hypothesis becomes a critical focus, as mathematicians struggle to determine if any size of infinity exists between the set of natural numbers and the set of real numbers. But the ladder of infinities doesn't just go up. It reaches a point where our basic tools simply fail. There are some cardinals so large that their existence cannot be proven using standard set theory. These are not just bigger numbers, they are anomalies in the mathematical landscape. In practice, propositions regarding their existence are used to measure how much one must assume beyond ZFC, the standard axioms of set theory, to prove certain results. It's a humbling realization. We've built a system of logic, yet there are peaks of infinity that the ZFC axioms simply cannot reach, forcing us to decide how much we are willing to accept as truth without a formal proof. We began with the simple act of counting, 1, 2, 3, and ended up at the doorstep of the uncountable. Georg Cantor transformed infinity from a poetic, vague notion of endlessness into a rigorous, structured hierarchy. Through Aleph-Null and the diagonal argument, we now know that the mathematical universe is not a single monolithic void, but a tiered architecture of different magnitudes. However, this structure leads to a startling conclusion. While we can define the cardinality of the continuum and the real numbers, the vast majority of these numbers are actually uncomputable. This means that while they mathematically exist, no computer program, no matter how powerful or how long it runs, can ever access or calculate them. We are left with a mathematical reality where the most common things in the universe are those we can never actually touch.